Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning. Today we will examine animal locomotion from a biomechanics perspective and focus on the physics of walking, flying, and swimming. I want to start with walking because it gives us a clear view of ground reaction forces and center of mass dynamics. When an animal walks, its center of mass follows a roughly inverted pendulum arc during the stance phase. In this inverted pendulum model, kinetic energy is exchanged with gravitational potential energy. That reduces the metabolic work required per step, compared with simply lifting and lowering the body on each stride. We also use the term duty factor to describe the proportion of the stride that a foot is on the ground. A duty factor above 50% indicates a walking gait, while lower values indicate running gaits. Elastic structures such as tendons and aponeuroses play a major role in saving energy. A famous example is the kangaroo. During hopping, elastic energy stored in the Achilles tendon is returned each bounce, reducing metabolic cost. Cheetahs, in contrast, use flexible spines and limb protraction to increase stride length at high speeds. That is an example where morphology couples to kinematics to maximize center of mass velocity during a gallop. Turning to flight, the physics shifts to managing lift and thrust against drag and gravity. For steady gliding, lift must balance weight and thrust must overcome drag. I want you to picture two extremes. Albatrosses use dynamic soaring and low wing loading to exploit wind gradients for near-effortless long-distance flight. Hummingbirds instead use high wing beat frequency and active wing rotation to hover. We measure aerodynamic performance with non-dimensional numbers. Wing loading, which is body weight divided by wing area, helps explain why large birds soar while small birds hover. The Reynolds number also matters. Small insects operate at low Reynolds numbers, where viscous forces are significant and unsteady aerodynamic mechanisms such as delayed stall and weight capture become important. An important dimensionless number for propulsion efficiency is the Strouhal number. For many cruising swimmers and flyers, the Strouhal number falls between 0.2 and 0.4, indicating an efficient vortex shedding pattern. Swimming presents different constraints because buoyancy and fluid drag dominate. Fish use body undulations. Anguilliform swimmers, like eels, undulate most of their body length, while carangiform swimmers, like mackerel, concentrate motion near the tail. The wake behind a swimming fish contains alternating vortices. Efficient thrust arises when these vortices are shed in a coherent pattern that transfers momentum rearward. Comparative studies link morphology to locomotor strategy. For example, tuna have stiff bodies and lunate tails suited to continuous cruising at high Reynolds numbers. On the other hand, reef fishes have deeper bodies and use pectoral fin-driven swimming for maneuverability. Across modes, power demands scale with size, but not linearly. Small animals typically use higher relative power and higher flapping or stride frequencies. Large animals rely more on passive mechanics and elastic storage. We should also consider environmental interactions. Ground compliance affects walking energetics. Air turbulence affects flight stability. Water viscosity, and temperature change swimming performance. Before I finish, let me give you a short case study. Researchers measured metabolic cost in ostriches and found that during running, elastic structures stored and returned a significant fraction of mechanical energy. This reduced the measured oxygen consumption compared with expected values based on muscle work alone. To summarize, whether walking, flying, or swimming, animal locomotion hinges on managing forces, exploiting elastic structures, and matching morphology and kinematics to fluid or ground environment. Understanding these principles helps engineers design better robots and informs our knowledge of animal ecology. That concludes the lecture. Remember the key terms we used, like center of mass, duty factor, wing loading, Reynolds number, and Strouhal number, because you will need them for the lab and exam.
Listen again to part of the lecture, then answer the question.
When I say that tendons act as springs, I mean they store and return elastic energy to reduce the metabolic cost of locomotion.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.